let's look at this picture. Are the triangles shown similar? How do we know? Well, what triangles do we see here? Maybe we draw them separate from each other. I see a triangle that's QSR, so I'm going to draw that separate from the picture, QSR. And I see another triangle inside that triangle, TUR. So it's a little bit smaller. I'm going to draw it separate from the picture, TUR. Well, what do we know also from the picture? This length from Q all the way to R is 2 and 5 put together, so that's 7. This length in the picture from S all the way to R is 3 and 7.5, so that's 10.5. And in the little green triangle, TR is 5 and UR is 7.5. Well, remember our 3 similarity postulates, theorems that we can check. Angle, angle, side, 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 or side, angle, side. Which can we use here? Well, first of all, I don't know the third side in either of the triangles. So side, side, side is out. I don't appear to know any angle measures, but remember that these two triangles came from being inside of each other and both used angle R. So angle R is congruent to itself by the reflexive property. It's the exact same angles, so I have that and that. So perhaps I can try to use side angle side and see if these sides that include that angle is proportional, if those sides are proportional. But it's actually quicker if we just notice that we've got parallel lines here. See these arrows? They tell us that these lines are parallel. Therefore, we have a pair of corresponding angles up here and a pair of corresponding angles down here. I don't even need those because once I know that angle Q and angle T are congruent to each other, now I've got angle, angle. One pair of congruent angles up here, a second pair of congruent angles down here. So by angle, angle, we just proved that these two triangles are similar by angle, angle. Well, what if we wanted to use side, angle, side? We could have done that too. Let's look at the sides that correspond, the small side with the small side. Well, what's 7 over 5? Well, that doesn't reduce, that's 7 over 5. How about we try the long side, 10.5 over 7.5. Type that in, that reduces to the same fraction, 7/5. So side, side, side can also prove that, not side, 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 sorry, side, angle, side can also prove that these two triangles are similar. Either way, we want to do it, angle, angle, or side, angle, side. We do see that triangle QSR is similar to triangle TUR by one of the postulates or theorems that we choose to use. Well, what I want you to see today is that by knowing that these are similar triangles, we can match up these corresponding parts, but they came from the fact that we have these parallel lines that are right here. See these parallel lines that are marked? That's telling us a lot about the picture. So I should erase them. So we can always match up the corresponding sides of the triangles, but in a picture like this, without even splitting it up into triangles, there's other types of corresponding parts that we can match up. Let's just take a look at something else besides the sides of the triangle. We matched up the entire side 7 to the entire side 5. Those are the smaller sides. But what if we look at this picture as a whole and match up just pieces of the sides? What if we match up this little piece that's on top with this little piece that's on the bottom and make a ratio from those pieces? So 2/3. 2/3 does not reduce to the scale factor of 7/5. Remember, when we match up the corresponding sides, that gives us the scale factor, and 2/3 is not equivalent to that scale factor. But it shouldn't necessarily be because it's not a side of a triangle, it's a piece of a side. We did the piece that's on the left with the piece that's on the left, going from top to bottom. What if we match up the piece that's on the right with the piece on the bottom that's on the right? So we did left with left, and what if we do right with right? Well, let's make into a ratio those two pieces on the right, 5 and 7.5. Let's find our calculators and type it into there. So I'm going to use this calculator because it's easy to make a fraction with this one. 5 divided by 7.5, and we can either enter right there or we can go straight into math and frac, and we see 2/3. Well, let's go back to this and see that's the exact same ratio we had from left with left. So the point here is the parallel lines gives us more opportunity to match up corresponding parts. What if instead of going left over left and right over right, what if we go in a different order? Let's try another pattern. How about left to right? So let's do 2/5. Not the same ratio that we had before, but that's because we're going in a different order. Instead of top over bottom, we're going left to right. Now let's do that on the bottom, left to right. 3/7.5. Let's go back to our trusty graphing calculator, and 3 divided by 7.5. We'll go straight to math, make it a fraction, and 2/5 is what we get, 2/5. So you see, going in an organized manner, left to right, we got the same ratio again. So this shows us that we may have similar triangles in which we can use the entire sides, but because of the parallel lines, we also now have corresponding pieces that are proportional. These parallel lines are dividing these sides proportionally. Let's write that down. Triangle proportionality theorem. If a line parallel to one side of a triangle intersects the other sides, then it divides the sides proportionally. So QT, one part of that side, over SU, so this piece over this piece in a ratio, will be the same ratio as TR, this piece from the top, over this piece from the bottom, TR over UR. That's one example of how the proportion can be written when the sides are divided proportionally. Or we could say QT, this piece, over TR, this piece, so going from left to right, equals, if we go from left to right on top, we go from left to right on the bottom, SU over UR. Basically, just matching up corresponding parts and going in the same direction. Now, the converse of the triangle proportionality theorem is very similar. If sides are divided proportionally, so first we see the proportional sides, then the line dividing will be parallel to the triangle side. Let's see how to use those next. In the diagram, this tells us segment AB is parallel to segment CD. So that's shown in the picture. AB is parallel to CD. BD is 15. So I'm going to put that in the picture, 15 for BD. AC is 10. So AC, put 10. CE is 18. CE is 18. Find DE. We'll put X there because we don't know it. We can make a proportion because we know these lines are parallel. So we can make a proportion that goes top over bottom, left only, 15 over 10, as long as we follow the same order on the other side, top over bottom, X over 18. Not the only way to do it, but a way that will work. We could have done left to right, so 15 over x and left to right equals 10 over 18. Either way we choose to do it will work because we're going in an organized manner. How do we solve this? Well, it's best that we simplify it first and then we can cross multiply. 15/10 simplifies into 3 over 2. So let's rewrite this as 3 over 2 equals x over 18. We can cross multiply from here. If you prefer to use a property, go for it. 2x equals 3 times 18, 54, and dividing both sides by 2, x equals 27. Well, they said find DE, so I will write DE equals 27. Let's look at the next one. In this diagram, segment PQ divides sides LN and MN into the lengths shown. Determine if PQ is parallel to LM. Determine if they are parallel. We don't know that PQ is parallel to LM. That was not given. We're trying to figure out if they are parallel. That's the converse of that proportionality theorem. Let's see if the sides are divided proportionally. So if we go in an organized manner, little piece on the left, we could put with little piece on the right, going left to right. So that would put 18 over 27. The question is it equal to going left to right along the bottom, 16 and 24? Little piece on the bottom, little piece on the bottom, left to right, as long as we're going in the same order. Is it equal to 16 over 24? Well, one of the best ways to do it is reduce both sides, see if it works, or maybe we cross multiply. So if we were to reduce both sides, 18 over 27, this divides by 9 and makes 2, this divides by 9 and makes 3, this divides by 8 and makes 2, this divides by 8 and make 3. So yes, they are equal. We could have checked it this way, 18 over 27 equals 16 over 24. We could have checked it by cross multiplying. What is 18 times 24? What is 27 times 16? Are they equal? Let's see. Clear out. 18 times 24, 432. 27 times 16, 432. So we see that both of these are 432. They're equal. Either way we choose to check it, it shows that the sides are divided proportionally. Therefore, determine if these lines are parallel. Yes, we will say PQ is parallel to LM.